Okay. Yeah, in previous lecture, as I told, we see that how we can calculate resultant force acting on plane surfaces, and those surfaces were either horizontal or vertical, submerged in a body of water. In this lecture, we are going to see how we can calculate resultant force acting on curved surface, like surface of this ball or surface of an arc dam. You see, this is an arc dam, and its surface has a curved shape, and therefore something like this. And we cannot use the rules that we have learned in previous sessions to calculate resultant force. What we should do in that case, we should find different horizontal and vertical component of resultant force first. Why? What is the reason? Let's see this figure and we can discuss the reason on this figure. Here you see an arc dam, for example, and this surface is not linear, and this is the water acting or pushing this surface. So as we already told, and we know that the pressure going deep into the water pressure increases, for example, at the bottom here, and we also know that pressure is always perpendicular to the surface. At this point, I have a highest or the greatest amount of pressure here acting perpendicular on this point. So looking at for example, this point at free surface, there is no pressure because there is no water depth, elevation of water on this point. And if we find pressure at several points, you can easily say pressure is equals to gamma H, and you can draw one of these pressure tensions. These are tensions, and then when you mix all these points together, when you draw this pressure distribution line, you will see that this line is not linear. Therefore, you cannot easily find the area under this pressure diagram. And this is why we first try to find horizontal and vertical component of the resultant force, then we can find the resultant force. For curved surface, the pressure force is divided into horizontal and vertical components. The vertical force, Fy, the vertical force. What is the vertical force? The force that acts in y direction. We will assume this is always our y direction is in that direction. For example, this is our x direction, and this is our y direction. Therefore, we will have vertical force or Fy, or sometimes you will see I show it with Fv, F sub v, and horizontal force Fx. What I mean by vertical and horizontal force, let's show here with another color. For example, we can say that, okay, this is the resultant force. Okay, this is the resultant force of this pressure diagram. It has definitely an x component. This is our x direction based on this direction, and I showed it with F sub x, or horizontal force, and this is y component. Actually y component like this, and it is called F vertical or Fy. And here you see that the horizontal force In the next slide, we will see the definition of horizontal force. Let's continue with the, vertical force. Let's continue with the horizontal force. The horizontal force, Fx, equals to the pressure on the vertical plane surface projected by the curved surface. The resultant force is a triangular combination of the horizontal and vertical parts. Yes, here Fx equals to Pc dot A. What is Fx? Here we see that it says that we should find projection of this curve on x direction, on y direction to calculate Fx. What is projection? Let me show you. For example, this is my curve, okay? This is my curve from here to here. So its projection on y direction, this is my y direction actually. And its projection could be this line. From here to here, one point we have, another point we have here. This is, therefore I have this, from here to here, is the projection of curve on vertical y-axis. Therefore, any force acting on this surface can be used. Any pressure acting on this surface can be used to calculate Fx. What does would be in general? Okay, I can now I can find the projection of the pressure on these vertical surface, like this. Then I can use this diagram to calculate Fx, this value. And you, from your previous lecture, you know that Fx from the vertical surface equals to Pc times area. Pc is pressure at centroid. And where is the centroid of this vertical line? Is its middle point here. Therefore, Fx clearly can easily can be calculated using Pc times area. Which area? Area of this vertical projection of the curve. It means that if the height or depth of water is h, area will be h times width of the dam, which is the perpendicular to your monitor now. Yeah, this is Fx. And how about Fy, vertical or vertical force, y component of F? For y component, what we should do for vertical component, the resultant force is equals to weight of real or imaginary water above the curve. Let's see here another example to discuss what I mean by real and imaginary water on above the curve. Here I have the curve, and I'm going to calculate resultant force, this force, this force, resultant force acting on this curve. In previous slide, I said that, okay, you should find first Fx and Fy, then calculate this resultant force through this formula, square root of xx squared plus Fy squared. Okay, for Fx, what we should do, we should find projection of the curve on y-axis. This is my curve, its projection will be this line. Okay, therefore, this trapezoidal diagram shows the distribution of pressure that acts on this curve. In other words, if you calculate the area under this trapezoidal pressure diagram, you can find Fx. Okay, it would be easy to you. How? You can find pressure at here, which equals to P times gamma times H. H is the depth of water here. So pressure at this line at this dashed line equals to gamma times this value. This is my H. And pressure at the bigger base of this trapezoid equals to gamma times entire H, yeah, entire. Then you have this trapezoidal, the lengths of the bases are at hand, so you can find fx. We will see some examples and I will show you how you can find this fx. For the fy, actually fy is nothing than weight of the water above the curve. What is the weight of the water above the curve? Weight equals to gamma times Wm times G. Therefore, or gamma times V, you should find volume of water above the curve. So which water we have above this curve? This water. This is the water above the curve. This is real water because you see, yeah, there is a water. So you can find this volume and multiply by the specific weight of the water. It gives you weight of the water and it would be your Fy. How about in some shapes, some conditions like this curve, a weight of the water above the curve is imaginary. For example, you see, this is my curve, and I know that Fy is this component because my F is this. I have such a, for example, assume that this is, for example, my resultant force, and to find this resultant force, I should calculate Fy and Fx, then use this formula, okay? For Fx, the problem is easy. I have two ends of this curve, and this line is the projection of the curve on y-axis. Therefore, assume the problem changed to a simpler one. To calculate resultant force on vertical surface, you know how to calculate this Fx. So come to check how we can find Fy, or vertical force acting on this curve. For Fy, I told you should find weight of the water above the curve. Okay, if you check the above the, this is my above the curve up to water surface. Let's show you in that in this way. So my curve starts from here and ends at this point. Therefore, this is the water level, you see. So I have an imaginary water. I assume there is the imaginary water here, and I have to find the weight of this water to calculate Fy. How to find? Easily. To find the weight, you should find the volume of this green area or area times V gives you volume. Then by multiplying the volume to gamma, you can find weight of the water above the curve. This is, as I told, imaginary water, and it gives you Fy. Then using this formula, you can calculate entire or resultant force. Okay, so if we want to mathematically express a formula for Fy or vertical force, we can say Fy equals to gamma times V. Which V? Water above the curve. It can be real or imaginary, like this green one as an imaginary and this blue one as a real water above the curve. Okay, any question?
No, teacher.
Okay. Let's use this concept to solve an example, then it will be more clear to you. Here we have a sector gate of radius 4 meter and length 5 meter, controls the flow of water in a horizontal channel. For the equilibrium condition shown in this figure, determine the total thrust on the gate. Here, this is our gate. You see, this is the gate, and its surface has a curved shape, okay? And the question asks you, okay, find the thrust or pushing force. Because of this water, we have a pushing on this force. And it is possible due to this connection to gate can be open, goes up, and some water released. And now we are, the question asks, how much is the resultant force acting on this gate? So let's, as I told, this is a curved surface, and to find a resultant force, assume this is, for example, my result. I assume this is resultant force, okay? And to calculate this Fr, I need to find the Fx and Fy. Let's see how we should solve the problem. First, the horizontal component is should be calculated. I know that the horizontal component equals to Fx equals to Pc times A. What should I do? I should find, to find horizontal component, I should first draw the projection of this on y-axis. This is my y-axis, yeah? Projection means, for example, this line. This is the projection. Assume this is a vertical line. And here I have a linear distribution of pressure. Sorry, not starting by 0. Because I have water above this line. And I should correct what I draw here. Let's draw it again. And yeah. Here, this is my vertical projection of this curve, and I have a pressure here with the value of gamma times h. H is 1 meter given, and another pressure here. Therefore, if I linearly connect these two pressure lines, this gives me pressure diagram like this. And this is the distribution of pressure on this vertical projection of this curve, and the area under this diagram gives you Fx, or Fx equals to Pc times area. You can easily use the equations of the Pc times area. What is the Pc pressure at the centroid? Where is the centroid of okay. Where is the centroid of this line? It's middle. Okay, so pressure equals to gamma times HSC. HSC centroid is half of this depth, or half of the d. Plus 1, we have 1 meter above the D, and area again would be D, this line, because we are thinking about this projected surface, times V, or width of the gate, which is perpendicular to your screen. So here to calculate D, half of D, or what I did, D, if you see, I have a triangle here, yeah? I have a triangle here, and this angle was given. And the radius also given. The radius, the question said the radius is 4 meter, okay? Therefore, D equals to 4 sine of 30 will be this value equals to D. And for sine of 30 degrees will give you 2, yeah? Will be give you 2. Again, D is 2 meters. You can write D here. And W is 5 meters from the given information from the question. So width of the gate is 5 meters. And if you calculate this, you will see that the horizontal component equals to 6.2 kilonewton. So where is the point that this force inserted pressure center, not centroid, pressure center. And for pressure center, you know that we can use this formula equals to centroid plus momentum divided by y bar A. Y is again the centroid. A is area of this imaginary surface. And for the calculation of moment of inertia, you can this is the rectangle. You know that bh to the power of 3 divided by 12. B is width. Here B is the width of our gate, 5. H is D equals to D here, yeah, 2 meter to the power of 3, 12 divided by 12. Then times y bar. Y bar we already said that y bar is the half of D plus 1, half of D plus 1, which means 1 plus 1, 2 times area. Area 5 times 2. Therefore, this is 2.16 meter is the pressure center. So what does it mean? It means that pan, let's go to the pan. If here 1 meter and this entire D is 2 meters, 1.67 somewhere here. Maybe here. Therefore, this distance from the here to here is 2.60, and this will be the location of Fx. Okay, so in the next step, I have to find Fy. Okay, and Fy, as I told, Fy equals to gamma times V. V, what is the V, or Fy equals to weight of water above the curve. You see, again, I show here water above the curve with green, which represent the imaginary water, because actually above this curve we have atmosphere. But to calculate force acting from water, we should consider this volume. So now the question is how we can find this volume. Do you have any idea? To calculate this volume, we should first find this area, then multiply it by 5 meter, because the width of gate is 5 meter. To find this volume, I think that I can calculate, for example, area of a big rectangle like this. then remove the area of this area. Or let's how I solved here. To calculate this area, I need first to know what is this distance from here to here, okay? And from this figure, from geometry of the figure, you can find that, okay, here I have a rectangle, I have a triangle, sorry. And if and I know that this length or radius of this circle is 4 meters. Therefore, this from here to here would be 4 cosine 30. So this blue area is at hand, and I know that from here to here is 4 meters. Therefore, this distance, or AB distance from here to here, that I need to calculate this value, okay? AB equals to 4 minus 4 cosine 30, which equals to 0.53 meter. Okay, I have this length. Okay, what I need again to calculate this volume. Okay, I know, the more area should be calculated. How I solve this problem, I show you here. Fy, or weight of this water, equals to gamma and volume. Volume width times area. Therefore, from here to here, this term shows this area. And for calculation of this area, I use two terms. One sub-area, the another sub-area. The one sub-area gives you this value AB, this value times 1, or gives you this area. Gives you this area. The other terms will give you this. If you check this term, I calculate a bigger area minus a smaller area. It shows you this, I calculate a bigger area. What is the bigger area here? PR square divided by PR squared divided by the ratio of this angle to the 38. This gives you entire this area. It means that if I have a circle here, yes, and the area of that circle equals to PR square. If I find this ratio, 30 divided by 360, it gives you this area. Minus, to find this, to find this segment, what should I do? Let's show with this color. I can calculate, I already calculate this segment, this sector of the circle. Then I should remove this part. I should remove this orange part, yeah? And this orange part is nothing than a triangle with the side of 4 cosine phi, this value, and base of d, 2 meters, divided by 2. Therefore, this part shows my rectangle area. And now, in total brackets, I have the area of yellow, of the green, or green area, or imaginary water. And it would be my Fy equals to 61 kilonewton. And therefore, now I have my X and Y components. To calculate Fy, I can use the formula that I showed you, Fr, or resultant force, equals to square root of Fx x squared plus Fy x squared. This is my Fy. So I know that Fy is always perpendicular to the surface. Therefore, it should pass from the centroid of this circle. And however, so far I don't know what is the alpha. And if you have your Fy, your Fx, the alpha can be found through the arctangent of the Fy over Fx. And if you put those values, you need to calculate arctangent of 0.30 and equals to 17.5 degree. This is entire process of calculating force acting on curved surface. If I'm going to summarize it, let's say easily, to find resultant force on curved surfaces, you need to find components, vertical and horizontal components of the force first. The horizontal component, to find horizontal component, you should find the projection of the curve on y-axis. Then you have the problem changed to to calculating pressure force acting on a vertical plane surface. Then you can find Fx. To calculate Fy, or vertical component, you need to find the volume of water above the curve. This volume can be imaginary or real water. And after finding the volume, you multiply it by the gamma of liquid, and it gives you weight of the liquid above the curve. Now you have Fy and Fx. You can use this formula to find resultant force. And to draw the force like this, you need maybe one angle like alpha. You can find it through arctangent Fy over Fx, and you always should be careful that your force is perpendicular to the curve. Yeah, this is all about the resultant force. Any question so far? Okay, so the last part of this chapter is buoyancy force. You know, we talked about the force acting on any object in the water. The object can be either horizontal, vertical, or curve, and we can calculate the force acting on water. But we have the buoyant force acting on an object which is also equal to the weight of water displaced in the tank. For example, if this tank is full at the beginning, when you put some object, something into the water, some of the water will move out. And the weight of that displaced water is called buoyant force or buoyancy force. Here in this figure, you see that the reason because any object wants to go into the water is weight, its weight, okay? And buoyancy force is a force against weight, and force from water to the object upward like this, that that resists falling the object into the water. If you have a cork, you see in this figure we have a cork. It is floating on the water. It means why? Because in this situation, weight and buoyancy force makes a balance, and the cork is floating because weight is too less. Therefore, it's equal to buoyancy force. Maybe for the case of wood, a bit more of the of part of this wood goes into the water, because if it goes a bit more than cork into the water, buoyancy force increases, because the displaced water amount increases, and equilibrium condition of balance is happens when some part of this wood is within the water. How about the iron? You know, iron is too heavy, and automatically what is amount of buoyancy cannot either keep the object in the middle of water or on the surface, like these two conditions. And it says that, for example, this figure says that, yeah, weight or gravity force is higher than buoyancy force. How to calculate buoyancy force? Actually, I explained. To calculate buoyancy force equals to weight of displaced water. You should find how much water displaced, then multiply it with the gamma. And you see the formula given for buoyancy force is very similar to the one that we use to calculate vertical force acting on curved surfaces. Yeah, this is also about buoyancy force, and that's all for today's lecture. Do you have any question?
No, sir. Thanks.
You're welcome.